Thank you very much, Yves, for this introduction. Thank you all for inviting me to give this this lecture today. So the title I use, Present and Future Photovoltaic Solar Cells. Of course, we need to talk a little bit about the past to better understand the present and the future. Just a few words to introduce myself more in detail. As Yves said, I am from INSA Lyon at Institut of Nanotechnology of Lyon. My research deals with photovoltaics for more than 20 years now. So I started to work on PV in the previous century. So it's quite long. I mainly work now on crystalline silicon solar cell technologies and development of new processes, new materials. So my main activity in the past 10 years was with, you can see here, nanowires of 3-5 materials for an efficient light trapping of the light. Here is the outline of my talk. I will make an introduction about the motivations and make the link between the energy countryside today and so the motivations to use photovoltaics. I will then introduce photovoltaics solar cell, explain briefly how it works, and then I will focus on fabrication technologies and the two main technologies, the old one and the new ones and the future ones. Okay. And in these future technologies, I will focus on what we call the tandem solar cell, combining silicon plus another material to have a better use of the solar spectra. Okay. If I have time, I'll say a few words about materials challenges also. As we are very few people, don't hesitate to interrupt me or to ask questions during the lecture. We don't need to wait the end of my talk. Okay. So I will start this presentation with two very famous slides. The first one showing evolution of human demography in the past 10,000 years. And the measurement of carbon dioxide in the atmosphere, so a measurement which is done in Hawaii Island from the end of the 1950s. At the beginning, it was not easy to show a trend in the first year of the measurement. What you can see mainly is the change in the atmosphere concentration depending on the season. So in winter, you have more CO2 than in the summer, I mean winter and summer for northern hemisphere countries. But after a few years, it was clear that there was a strong increase year by year of this carbon dioxide concentration in the atmosphere. So why it increased? Because we emit every year more and more carbon dioxide in the atmosphere. So this curve is quite nice. Maybe now you can study this in history for baccalaureate, for instance. You can see studying this curve all the history of the 50, 60 previous years with oil crisis, dissolution of Soviet Union, etc., etc. Of course, this led to an increase of the temperature, but you all know about this. What you know also is that a few years ago in Paris, there was an agreement between most of the countries about keeping the elevation of temperature below 2 degrees. But if we want to fulfill this agreement, we know that we are able to emit only this quantity of carbon dioxide more in the atmosphere. So it's 800 gigaton. Okay, so there are several scenarios possible if we want to reach this this objective by 2050. But as you can see, the changes should be very, very drastic. Now, coming to the link with solar energy, you may know that most of the carbon dioxide and greenhouse gases emission comes from the energy sector. It's about 80% of the greenhouse gas emissions coming from energy sector, which is very, very important. So this energy sector, what kind of energy do we use at the moment? You can see the evolution among the past 200 years. If we look at 2019, 2020, so now about 80% of the primary energy is coming from fossil sources, biomass, coal, oil, and gas. And only on the top of this curve, we can find nuclear energy, solar, wind energy, and other renewables. So this is primary energy. So you know that what is important is what kind of energy we use. So this is what we call the final energy. It is that which is supplied and used by the consumer, like the gas, like the electricity, domestic fuel oil, etc., etc. But in order to use this energy, we need to extract, to store it, to transform it, and we need also some energies to do this. So if we combine everything, we get what we call the primary energy. In this talk, when we talk about energy, I will not use joule, but I will use watt hour or gigawatt hour, depending on the size of the system I will consider. And this is the same for the power. I will use kilowatt or terawatt. So now let's focus on electricity production. 60% of electricity is still carbon-based in 2023, mainly coal, gas, and a bit of oil, and only nuclear, hydropower, bioenergy, and renewables for 20%, for 40%. Yep. What you can see on this graph is that hopefully the coal energy provided by coal, well, we don't see it clearly, but it seems that it's becoming to stabilized, and it should decrease in the next year. However, the use of gas is still improving today. Nuclear energy is quite stable in the past 20 or 30 years. There is maybe a lot of debate with nuclear energy. I will not enter in it today. About hydro energy, what is important to see is that the quantity of hydroelectricity is almost constant if we compare with the big increase of the total amount of electricity. We can see that hydroelectricity is quite constant. It does not increase so much. So there is not so much new space available to build some dams and so on, especially in Europe, for instance. And on the top here, we have wind and solar energy that are actually increasing quite a lot quickly. Maybe not enough quickly, but it's quite positive. Just a few seconds on this slide showing if we start from primary energy, so we have fossil energies and renewable energies here on the right, and on the bottom we have the final energy, what we use. So here this is the oil, the gas we will use for transportation, heating of buildings and houses, and here is the electricity. What is important to see here is that we can make electricity with many sources of primary energy, but during this process, we are losing a lot of energy. Here, the conversion is only 30%, or even less. Okay. Regarding the objective to decrease the emission of carbon dioxide and other greenhouse gases, European Commission make some plans for the future and propose several scenarios. I will introduce you two scenarios possible. The first one is, it's not business as usual, but it's economic transition scenario. So fossil fuels will still play an important role in European energy mix in the longer term. As we can see here, so today we have oil, gas, and coal. We will reduce coal, of course, but gas and oil will still be used in 2050. Okay? With increasing solar and wind energy, we will be able to decrease the emissions of carbon dioxide by 30%. This is the primary energy. If I look at electricity, so the electricity will be much cleaner in 2050 within this scenario. We will have 70% of electricity coming from renewable energies. Now, if I look at the net zero scenario, so it means this is zero carbon dioxide emission by 2050. In this case, we have to completely eliminate coal and gas and oil for the generation of electricity and also for transportations. Okay. In Europe, the idea is to have a mix of solar and wind, and maybe a larger part of wind energy in Europe. And if I look at the production of electricity in this scenario, we will need much more electricity. So we will get this electricity from wind energy, onshore or offshore solar energy, biomass, hydro, nuclear, hydrogen, still a little bit of gas, okay, and the use of batteries. So we have to multiply by a factor 2 the production of electricity. In this scenario, so we will start by decreasing by 50% emission of carbon dioxide in 2030 compared to 1990, which is a reference year for this calculation. So what is important to remember, it's that decarbonation of our societies implies more and more electricity. So what will change between what we are using today compared to 2050? So we will use well, the double of electricity, even more. We will stop using natural gas, okay? And we will replace this gas by biogas, hydrogen, electrogas. Oil will be suppressed, almost suppressed. We can keep a little bit, especially for planes. And oil will be replaced for cars by biofuels, electrofuels. And yeah, that's it. So electrofuels, it means that this is fuels that are manufactured using the carbon dioxide we capture in the atmosphere. And thanks to the use of electricity, of clean energy, we will reduce this molecule and we will form some carbon-based molecules like ethanol, etc., to be used for the transport. I would like to now to make a focus on the French case. We're going to watch what is the production of energy today in France. So there are several questions that you can think about before looking at this. It's what kind of mix do we use today in France? What is the share of nuclear generation and renewables? And what was the evolution between today and 10 years ago? So I will see if I can. So if it can works. Ah. Ce site n'est pas compatible avec votre version de navigateur. Bon, j'ai pas essayé tout à l'heure, j'aurais dû, ouais. Ouais, c'est bizarre. Sauf qu'on ne voit pas à l'écran.
Je ne l'ai pas. Hein, On va arrêter le partage. Si ça marche.
Bon, bah écoutez, ça marche pas, c'est pas grave.
Oh, j'avais bien noté que vous vouliez faire.
Bon, c'est pas grave.
C'est ce qu'on vient de faire. Comment? Si, si, sinon on ne ferait pas la vidéo. C'est pour ça que pas censé avoir.
Bah, oui.
RTE, ils veulent pas.
Bon, c'est pas grave.
Ils votent.
Non, mais c'est le seul que que j'avais prévu.
Service.
Non, 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 c'est pas grave, c'est pas grave. Alt F5.
Ouais. Mais c'est juste que j'aurais pas le partage si je fais Alt F5.
Ah oui, c'est vrai.
Et...
Okay, so sorry for this trouble. I cannot. Ouais, et puis là, ça marche plus. Okay.
No.
Okay. So you can have a look by yourself on this website. So RTE is the company, public company that control not the production but the distribution of electrical energy in France. You can see that on this website you can get many informations about the production at the moment on live. You can have the data for the past 10 years. You can see where the energy is produced, in which region of France, what are the exports and imports to and from the neighboring countries. Very interesting. And you have the same kind of website on for Germany, which is also a very interesting case, especially when we talk about energy transition. So what we could see France. So it's not really sunny at the moment, but in summer you should have about 20% of electricity produced by PV at noon, of course. The production is very centered at midday. You can see that the wind power is relatively constant over a day. You can have some changes, of course. You can have some local changes, very important local changes, but on a country, on a wider zone like a whole country, it's quite stable. You can see that France is a very specific country because it relies on nuclear energy as the main power source. So it's about 70% of the production of electricity in France. Last year, it was less because we had many problems with corrosion in these power plants. So many, 50% of the plants were turned off last year. So it's getting better now. So we come back to 70% of the electricity production. So nuclear energy is the base load for France. We have a lot of solar energy during the daytime, but to adapt the production of electricity and the consumption of electricity, we use the gas and hydroelectricity to adjust the production with consumption. France is also now export a lot of electricity, maybe 5-10% of its production. But last year, because of this trouble with the nuclear power plant, we had to import some electricity from Germany and Great Britain. Electricity, it's a specific energy that has some drawback compared to oil, for instance. The big problem is that this energy cannot be stored. Once we produce it, we need to use it. Okay. Of course, there are some batteries, but batteries are not as efficient of fuel. Batteries cannot last long time. You have to use your electricity very quickly if you don't want to lose it. So let's come back to the world production of electricity in the world. So as I said, so coal production is decreasing, gas is still increasing, hydroelectricity stable, nuclear slightly decreasing, and renewables are increasing a lot. So we have several sources to produce electricity that are available. We are going to compare these sources. Some of you maybe are not aware of this, but if we compare the power capacity of the sources, first, nuclear energy, one power plant, it's about 1 gigawatt, a little bit more, so let's say 1.5 gigawatt. Wind turbine between 1 and 5, depending on the size. So the standard one today, it's 3 megawatt, but they are getting higher now. So we can go to 5 megawatt. And for offshore wind, offshore energy, we can continue to increase to 10 or 15 megawatt one wind turbine. For hydroelectricity, so it's very depending on the size of the dam, from few megawatts to few gigawatts. There is a huge dam in China that can produce more than 20 gigawatt. And solar electricity, solar photovoltaic, you can have on rooftop. So for individual houses, so you will have 2 to 3 kilowatt power plant. That you can have also some, we call this utility scale power plant. You have a very large one in China, in India, with 1 gigawatt. So the question, if we compare 1.5 gigawatt of nuclear energy with 1.5 gigawatt of solar energy, this was the biggest photovoltaic plant in China, in Gobi Desert in 2018. But there is some new power plant now in India, and a new one again in China, which is already the double of the previous one, so almost 3 gigawatt. I don't know the size of this one, but it's 7 million of solar panels in the desert. So the question is, can we replace 1.5 gigawatt of nuclear energy with the same power of photovoltaic energy? You know the answer. Huh? It's different because of intermittence of the source of energy. So the sun is not lighting during all day. You have to alternate night and day. And between two successive days, you can have a very difference in the very different productions of electricity. And this is the same here for the wing during 1 week it was in February 2014. So we use this term intermittence problem, but actually we should use instead of intermittence, variability. Intermittence, it seems that we cannot predict the quantity of sun available from day to day. Actually, we can quite easily predict the energy we will be able to receive from the sun or from the wind, and we can adapt. We know in some day with no sun or with less wind, we have to use more nuclear energy or more gas energy, etc., etc. So to compare several sources of energy, we use the capacity factor. This is the ratio between the energy produced by the plant during a period of time divided by the amount of energy the plant would have produced at its full capacity. So, for instance, nuclear energy can work day and night, anytime. It's only 80% because sometimes you need to stop the plant. You need to do some maintenance. For hydroelectricity, it's the same, 30 to 50%. Coal, okay, around 50%. Solar, it's between 10 and 20%. It will depend on where you are. In south of Europe, you will be at 20%, but in northern Germany, it will be only 10%. So in Lyon, in Saint-Étienne, almost the same. We can say it's about 15% the capacity factor. So knowing this, knowing the power of your power plant, knowing that 1 year is this number of hours, you can calculate the production of electricity, so by 1 nuclear power plant, and by 6 photovoltaic power plants with the same initial power. Okay, here is the capacity factor. Okay, so you need 6 power plants like this of PV to replace 1 power plant of nuclear energy. But it's not fully true, of course, because at night you produce nothing at all. So you have to combine photovoltaic plants with other sources of energy, wind energy, hydroelectricity, gas plant. It can be electrogas, of course, and especially for France, we will continue to use nuclear energy even in 2050. Okay? Of course, with this new scheme for production of electricity, we need to pay much more attention to the management of the electric grid. It becomes more and more complex because we have to adapt constantly production and consumption of electricity. So this is electricity production of renewable energy in the world. So it's mostly PV, wind energy for 1/4, and hydroelectricity from another quarter. Okay? But you can remember that the main increase in the world is due to photovoltaics installations. I will not develop this part. There is a very common question about the possibility to have a 100% renewable electricities in France, in Europe, or wherever. It's a very complex question. We have to take into account several factors. Sorry for this French language slide. If you are interested in this topic, there is several international studies showing that it may be possible to have only renewables. Of course, we need to pay attention to our use of electricity to avoid the peak electricity peak at 7 p.m. or 8 p.m. 8 a.m. in the morning, where everyone wants to use electricity at home, but there are some solutions. So now, is there any questions about this introduction? Yes. Yes, this is the sorry. This is the case for Europe. So Europe, you can see that maybe 60%, 70% of renewable energy will come from the wind. Well, it's prediction done in 2020, and what happened in 2050, we don't know. We try to give some trends, of course, but in Europe we have a lot of coast with very windy coast, so it makes sense to have a lot of wind energy in Europe, but wind energy suffer from especially recently from a bad opinion of population. They say that it's ugly, our countryside in France are so beautiful. We should not add some high wind turbine near the coast or anywhere. So maybe it's very too optimistic for wind. Okay? But I think if the objective, I think we will be able to add to increase the share of photovoltaics in Europe. Okay? One of the main advantage of photovoltaics is that it's very simple technology. I will show you. It's very easy to make to fabricate some solar cells. It doesn't require a very big knowledge and very. It's not like dealing with a nuclear power plant. Every country, almost every country, can install a production center of PV panels. It's easy to install. You can install by yourself your PV on your rooftop. And this is very important, especially for developing countries in Asia, Africa, and so on. Yes. No. Well, maybe we can also generate electricity from the sun with what we call solar thermal electricity. We concentrate the sun, we heat a fluid, it can be water or anything, and we produce some vapor. And with this vapor, pressurized vapor, we can work a turbine and produce electricity like this. There's many possibilities, very interesting, funny possibilities also, but it was carefully studied in the past 10, 20 years. But you will see with the development of photovoltaics and wind energy that become less and less expensive than 10 years ago. There is almost no interest anymore to produce electricity from thermal energy. Of course, you can use this to produce some hot water for on the rooftop. Okay, it is also, this is interesting, but to directly produce electricity, almost not sense today. Oh. Okay. So to illustrate what I just say, I will say a few words about the cost evolution of the PV modules. In 2022, here as the photovoltaic market, so installations of PV modules is mainly in Asia at the moment, more than 50%, then Europe and North America. Production of, sorry, I don't have this slide to show that the production is also mainly coming from Asia by 70–80% today. It was a big change in the year 2005–2010, where the production was mainly in Europe. It moves to Asia. The advantage of this change is that we were able to see a very important decrease in the fabrication cost of modules. The drawback is that we lose PV industry in Europe during these past 15 years. This is something which is changing. We said a few words about this in my conclusion. Okay. Yeah, so China is the most important PV market. Here you can see the installation, the annual installation of photovoltaics. So in 2021, we installed 200 and something gigawatt. And last year, we installed 250 gigawatt. It's very important if you remember the values of the nuclear power plants and 1.5 gigawatt. Even with a factor of 6, this is very important. Okay. So few data in 2000. So when I started to work on photovoltaics, you cannot see here on this using this scale, but at that time, if we look what happened from 1990 2000, it was already exponential curve. Okay, so it's an exponential curve since 1990 actually, but during this period it was very still very small. So it's becoming very important only in the past 5–10 years. Okay, so in 2020, almost 4% of global electricity was produced by PV. I guess it's 5% today in the world. Here you have the top 10 countries. So as I said, China, European Union, United States. Yes, this is for installed capacity, and it's not production. So we have two kind of PV installations. We can, so in orange, we have what we call the rooftop installation. So this is individual installations, what you can install on the rooftop of your house, of your building, and what we call utility scale. This is a large area of photovoltaic power plant. You can see that the ratio, it's depending on the year, but maybe 40% of individual installation and 60% of utility scale. So I need some energy. Hein? Ah oui, pardon, il y avait marqué la batterie est faible. Ah bah oui, c'était débranché. C'était débranché. Ouais. Wow. Non, vous l'avez toujours. So about the price. About the price. So here, this is like prehistory of solar energy in the 70s. But even if you look at in the 90s or the year 2000, the price given in dollar or euro per watt, it was maybe 6, 7 euro per watt. I remember at that time when we asked some fundings to agencies or companies. We researchers, we used to say that we are going to develop a new technology to fabricate solar cells, and we will reach $1 per watt with this technology in the year 2010, 2020. And when we say this, we were not sure we will be able to reach this. But actually, and I think we never saw how fast would be the decrease in the cost. And today in 2023, well, I forgot to add it, but it's 25 cents a watt for crystalline silicon solar cell. So it's very cheap, and you can look at this price on this website. Why we had this decrease in the price? For two main reasons. So the first one is that we increased the production of solar modules. So it's logarithmic scale in both cases. So here's the PV module price versus production. This is what we call the learning curve, because it's historical data. And we can see that there is a trend. showing that we have a 20% price reduction each time we double the production of solar modules. Okay, and now we reach 25 cents per watt in 2023. Okay. Well, if you want, I can say talk a little bit more about this this curve. You can see it's not very fully linear. We can see there is three regions. Here, this is a historical trend. We increase production, so we reduce the cost. So for any kind of industries, during this period, it was quite stable, not stable, but reduction was quite low because of what we call silicon shortage. With the boom of photovoltaics, we need more and more silicon, but the raw material was not available. So there was some increase in the cost of this raw material. But after several years, many silicon companies installed some new factories, and then the cost drastically decreased. So two reasons, I said. So improvement of the production. And the second reason is many innovations in the fabrication of the solar module, in the quality of the solar module. You can see here evolution of PV module efficiencies versus years. So 15, 20 years ago, average efficiency was only 14%. And now in 2018, it was 18%. In 2023, it's almost 20% now. So this price of 25 cents per watt doesn't give you the good information. What is important is the price you need to produce some electricity, the energy you are going to use. So the price should be given in kilowatt hour. There is several ways to calculate this. The standard way is what we call the levelized cost of electricity, PV or any kind of energy. Before explaining exactly how it is calculated, I show you this curve. It's a quite old curve. I think it was drawing 15 years ago, but it's still we can still use it. It shows operating hours. So here this is Northern Europe, and here this is Middle East. We have a lot of sun here and a lot of clouds here. And here is the price. And of course, the price is decreasing when you increase availability of sun. So it was in 2010 here. You have some cost of electricity by, well, between 30 cents and 15 cents a kilowatt hour, depending on the geography. And in 2020, between 5 cents and 15 cents kilowatt hour. I don't know if you are aware of the cost of electricity in France today. No? How much? What is the bill when you pay every month electricity to EDF? You pay about 15 cents a kilowatt hour. It's a cheap price compared to other countries. In Germany, it's 25 cents, 30 cents in Japan. I don't know for other countries. 15 cents. Okay, we have to take into account, of course, the production, the cost of the production, but also all the expenses to bring this electricity to you, etc., etc. Okay, but now in 2020, the cost of electricity, production of electricity, can be as low as 5 cents per kilowatt hour. So it's quite cheap. A few words about this levelized cost of energy. So it's economic assessment of the cost of the energy generating system, including all the costs over its lifetime. So it takes into account, of course, the initial investment, how many euro you have to pay at the beginning to have your installation, operation and maintenance cost, the cost of fuel. For solar PV, there is no cost because the fuel, it's the sun. But if you compare with a gas power plant, and you need to buy some gas, and the cost of capital, you need to ask money to your bank, and this is also a cost. So it's useful to calculate the cost of generation of electricity from different sources using this. So you have a formula like this, taking into account all the parameters I just mentioned. This cost has to be calculated for 20 to 40 years. It depends, of course, of the lifetime of your power plant. This is something difficult for individual who would like to switch to photovoltaic energy and to install PV panels on the rooftop. As I said, the production of electricity is cheap with this, but when you install your PV panels, it's like you paid in one time all the electricity you are going to use for the next 20, 30 years. So it's a very important cost. It's not like when you pay your electricity every month to EDF. So you need to invest this money. So that's why there is still some support from the government to help people to install PV on the rooftop. So to come back to LCOE, here this is data from 2020 comparing LCOE for different countries and different energy sources, nuclear, wind, solar, etc., etc. I just focus on two data for France. Nuclear energy, so 30 cents. So taking into account everything. And for solar PV, 33 cents. So in the same order of magnitude. Okay. So you can check this website to see the evolution of this data. So LCOE is very useful, but it's also a poor means of comparing electricity sources because there is many costs that are avoided that you cannot that you don't take into account in your calculations. I will not go into details, but when you make these calculations, you have to really to well declare what are the boundaries of your calculation. Okay. Anyway, this is evolution of PV module price in Germany for individual installations. Yep, a decrease. at the same time, you can see there is two colors. So in orange, this is the price, I mean, the share of the module in the final cost. So it was 70% in 2006, and now it's less than 40% only. In blue, this is what we call the balance of system. So it takes into account all the components that you need for your PV installation, except modules. So you need an inverter to convert your current into alternative current. You need the mounting system. You need the wires to connect your installation to the grid. And of course, you have the installation work. Someone has to go on the rooftop and to make the installation. This is another slide showing the same. This is for USA. In USA, the modules are very cheap compared to other costs. What you can see is that even and what you can remember is that the share of the module in the final cost has decreased a lot in the past past years. Okay. Another data here. For an average of available countries, you can see the modules, it's only 37% of the final cost of your power plant. So the cost of the modules become less and less important in the final and total cost of the PV installation. What is the consequence? It's how you can continue to decrease the cost of the energy you are producing if the share of if the cost of the module represent only a small part of the final cost of the installation. On this graph, it's you have three colors, so it's three technologies, three kind of materials we are using to make the solar modules. In blue here, this is a monocrystalline silicon, so it's a standard material now. Here, this is a multicrystalline silicon. I will describe a little bit later. And this is other materials, it's amorphous materials, low-cost materials. We call this thin films. Okay. In the year 2000 to 2015, what was important was to decrease the cost of the module. Okay. So we use lower quality silicon, multicrystalline silicon, and high quality silicon show its share decreased. Okay, it's given in percentage. But since the cost of the module represent only a small part of the final cost of the installation, if you want to continue to decrease the cost of the energy you produce, you need to increase the efficiency of the module. And if you want to increase efficiency, you need higher quality material. So that's why now we are using about 90% of single crystalline silicon. And that multicrystalline silicon is becoming more and more rare in the production lines today. Last slide in this wide introduction, to prevent some questions that you may have, it's what we call the energy payback time. How many energy do we need to produce some solar modules? So it's in this slide, in this graph, you can see the cumulative production versus energy payback time. So how many years we need to produce energy to compensate the energy we need to fabricate the solar module. And you can see that in 2020, we are about 1 year. So we need 1 year of energy to compensate energy we need to produce a solar module. This is data for Southern Europe. So it's maybe 1.5 year in France and Germany. Okay? And solar module, you can use it for 25, 30 years, even more. Okay, so last point is it's solar modules may be not very nice in the countryside. Here it's somewhere in Spain, and this is true. It requires a lot of space. What we are developing now is what we call integrated PV. So in building, it can be on facades, it can be on rooftop, etc., etc. There is a lot of new design coming in the recent years. Not only the standard PV modules to help integrated the modules in the buildings. And last point, the PV modules, it's dark blue or black because it needs to absorb the light, of course. But there are also some possibilities to make colored modules. Of course, it works not as good as a black module, especially this one. This is a white solar panel. So this panel is reflecting the visible light, maybe 80%, but it still absorbs the infrared spectra. So efficiencies can be not so bad, 10 to 12%. It's not very good compared to standard modules now above 20%, but for building integration, it can be useful. It's white, but it can be any other color also. So I have 1 hour left. I will talk about very quickly about p-n junction and efficiency calculations. We show you how we fabricate the silicon material to provide wafers, and they say a few words about the 2 silicon technologies that we have in the past year, even if one has almost disappeared now. So let's start. So there is a very wide variety of solar cell. This is a very famous graph for PV researchers, giving cell efficiencies versus years. So we start from 0% and we go towards 50%. Very high efficiency. You have many colors. It's not to make it beautiful, it's to distinguish the several technologies that we have. So in blue, this is the crystalline silicon solar cell. There is 3, 4, 5 different curves, but I will not go into detail. What you can see here is that we have 25% in 1995, and it was constant during almost 20 years, 25 years. And now there is some new technologies emerging, allowing to continue to increase efficiencies up to 27%. The green is what we call thin film technology, so it's low-cost materials, but efficiency is still a little bit lower. In purple, you have the high efficient materials. It's mainly 3-5 materials, gallium arsenide, indium phosphide based materials. They are very expensive, but combining several materials, you are able to reach almost 50% efficiency conversion. And in the recent years, we can see emerging some new materials. So here it's organic materials, and here you certainly heard about it. It's what we call perovskite materials. So perovskites are a mix of organic and inorganic materials. And you can see they rise from 2010, 2015, but they are reaching now efficiencies comparable to silicon efficiencies. It's very promising. So I will go a little bit faster. So solar cell is the technology of fabrication of crystalline solar cell is very linked with the integer circuits technologies. We can find almost many of similar fabrication tools, but there is a very important difference. I want to be sure you understand it. Now in IT, you have wafers, silicon wafers of 300 millimeter size. On one wafer like this, of course, it depends on the application, but you have tens of billions of devices on the surface. And at the end of the industrial line, the price, the cost of the wafer can reach $30,000, $50,000. If you compare this with a silicon solar cell, almost same size, same material, which is silicon. So billions of devices here, and here you have only one device. It's a single PN junction, a single diode. And the cost at the end of the production line will be 1.5 or $1. Very, very cheap. So you have to keep in mind that low cost production, so low cost, the tools that we are going to use to fabricate this single diode is the cost of each technological step you want to use. You want to add in your process to improve the quality of the cell. You have to consider that low cost is really essential. With what kind of materials we can convert light into electricity? So mainly semiconductors, silicon, gallium arsenide, indium phosphide, and so on. Of course, you have also 2,6 materials like copper, indium, gallium, selenium materials. You have organic and perovskite. Photovoltaic effect so relies on the energy band gap of the material, of the semiconductor. So this is valence band, energy, the conduction band here. So you have a photon that's coming here. It will transmit, if it is absorbed, it will give its energy to one electron from the valence band that will be able to go up to the conduction band. Then the electron is free and is free to move in the material, and it can be collected from the outside circuit. Okay. There is several kinds of materials that can be used. Here is the efficiency versus the band gap of the material. Well, you can see that there is a maximum here in this range of energy. Silicon is right here. Gallium arsenide is here. And we can see for this material that we are not so far from the theoretical limit of efficiency. To calculate the efficiency, we have to take into account all the photons that are available in the solar spectra. So we have visible light, of course, but we have also some infrared light. And the main parameter will be the band gap. So for instance, for silicon, 1.1 electron volt, it corresponds to cutting wavelengths of 1.2 micrometers, so it's here. So all the photons here cannot be absorbed by this material, sure. But the photons in the visible range, they have an energy that can be higher than the energy of the band gap. So this excess of energy is useless for the photovoltaic conversion. If you use blue photons or infrared photons here, one photons will give 1 electron, but these photons will also deliver some extra energy that will be dissipated by heat. Okay? So for silicon, the maximum current we can obtain if we absorb all the photons here on the left side of this graph, it's 46 milliamps per square centimeter. So you know the principle of PN junction. I will not go into the details. P-type material, N-type material. So you have electrons in the valence band. When a photon is absorbed, it will generate electron hole pair. So the electron can go to the conduction band. It creates a hole. And thanks to the electrical field in the junction here, you can collect the electron in the N-type region. Okay. So we can schematize the solar cell in 3 parts. The base, what we call the base, this is 200 micrometer thick silicon material. We have emitter, N-type region here, very thin, 0.3 micrometer. We have the depletion region here. It's also a few hundred of nanometers. And depending on the wavelengths, the photons will be absorbed in the different part of the solar cell. So here is a schematic cross view of the solar cell, silicon material, anti-reflective coating in blue, and in dark it's the metallic contacts. When we to calculate the efficiency, we need to plot the IV curve. So without light, it's something like this. You know it. When we add when we add light, so we generate a negative current, photo-generated current, and then it translates the curve like this. Efficiency is given like this. We calculate the maximum electrical power we can generate. So it will be at this point, divided by the incident power of the light. And we like to use these parameters. Open circuit voltage, so this is the maximum output voltage we can get when we have a zero current. And here, this is a short circuit current where there is no voltage, but the maximum power is given for this couple of current and voltage. This is maximum and current and maximum voltage. And we may use also this factor, the fill factor, which is the ratio between these two power. Okay, so the standard open circuit voltage of a silicon cell, it's 0.6 to 0.8 volt. Here is the current and efficiencies in the range of 17 to 25%. Okay. What are the factors that influence the quantity of current you can generate? Of course, you have light intensity. More photons you have, more electrons you can provide. The light spectrum, but also the electron collection probability. Once the photon is absorbed in the material and generates electrons, you need to collect this electron. So the problem is that electron can recombine with a hole in this material before being collected. Okay? So to avoid these recombinations, you may have passivated surface. You know that in the surface of the materials, you may have many defects. And these defects can lead to recombination of electrons. Well. So a few words now about the silicon material elaboration. We start not from sand, as you may think, but we use quartz, specific kind of quartz. Theoretically, of course, we can use sand, but there's many impurities, and it requires a lot of energy to remove these impurities. So a few words about silicon. But from what is important is how we get this silicon. So we start here with a very an industrial process combining the quartz and carbon, and you will reduce the silicon oxide thanks to this reaction to produce silicon at very high temperature. It takes a lot of time, and during this step, you will produce your silicon, but you will also produce carbon dioxide. This is the most important part of carbon dioxide emission, and from PV industry, it comes from this step. Therefore, you need to purify this what we call metallurgical grade silicon. So you use a reaction with chlorhydric acid, and you produce trichlosilane. So it's a gas. It's done. It's done at 300 degrees, and then you will decompose this gas within this reaction. So it requires a lot of time, 300 hours at also high temperature. And you will produce high purity polysilicon rods of diameter 20 centimeter. So this is the way we produce semiconductor silicon, high quality silicon for the IT industry. For the solar industry, we may reduce this time because we don't need the same quality of silicon. So this is what we call the solar grade silicon. This is silicon which is specifically dedicated to the fabrication of solar modules. Once we get our silicon, we have two possibilities. We can make single crystal or multicrystalline silicon. So single crystal, it's perfect crystal like this. And multicrystalline, you have many grain boundaries that may affect the recombination rate of electrons in the material and reduce the final efficiency of the solar cell. Well, this is CZ Krozalski technique to produce the silicon crystal. So you have a melt of silicon. You have a germ, a nucleus of crystalline silicon, and you turn it. You pull out, and you will make the crystallization of silicon, and then you cut into circular wafers. For multicrystalline silicon, so you melt your silicon like this, so at this temperature, and then you reduce the temperature in the furnace on the lower part of the furnace, and then you will have crystallization from the bottom to the top. So it's in few seconds, but this you need about more than 1 day to fabricate this kind of silicon ingot. Once you get your ingot, you cut it in pieces. Okay. Then you slice. You make wafers from 150 to 200 micrometers. During this step, actually, it's important to know that you lose about 50% of the silicon because of the diameter of the wire. The size of the wafers was standard until recently. It was 160 millimeters square, and now we have more and more wafers with a larger size, and now we are starting to use them. So 21 by 21 centimeters. So we are increasing the size of the wafers. How do we fabricate the solar cell from the wafer? So first, you clean the wafer after slicing it. You make texturation. It's use chemical way. Then you diffuse some phosphorus into your P-type silicon in order to get the PN junction. You etch the edges to isolate your PN junction here. Then you deposit anti-reflective coating. Then you deposit your metallic contact and you heat up and you anneal the contact. So on the back side, you have aluminum. So aluminum, it's P-type material for silicon, and it will compensate the N-type material that was here before. Okay. Well, I will go a little bit faster now. I think it's not so interesting, this. Okay. So once you fabricated your solar cell, you will connect it in series with other cells to make the module. So a module, what is it? So it's your solar cell here that are deposited on a TEDLA, which it's a composite material. It's the base of the module. You have resin. It's EVA. That will envelop completely the solar cell and fix it on the TEDLA. And then you have your glass on the top of it. Okay, so this glass is very important. It has to be, of course, transparent to the light, and it will protect the solar cells from the outside atmosphere. So you have these two kinds of solar cells. This one is single crystal and multicrystalline solar cell. When you have a very efficient texturation step, it's very difficult to recognize multicrystalline solar cell. You cannot see almost cannot see the grain, but the difference between these two is here. It's coming from the fact that the single crystal, it's a circular wafer. So you cut it like this to have high density of material on the module. Meanwhile, for multicrystalline, it's more easy. You just put the square in the module. Okay, so this kind of solar cell is what we call the aluminum back surface field solar cell. It was a standard technology for the last 30 years, from the beginning of 90s. You can see it's very simple technology. What is the main drawback here? It's that when you have photons of several energies, so I will focus on this one. This is infrared light. Infrared light will be absorbed in the volume of the solar cell, especially near the backside of the solar cells. So you generate one electron here, but this electron, it has to be collected in the emitter region. But this is p-type material, so you have many positive charges, and it can lead to recombination of electron hole. The electric field that is here is not sensitive for the electrons generated so far in the volume. You may also, so the electron is recombined and it is not collected. So that's why when we deposit aluminum, we have a high temperature step in order to make diffusion of aluminum into silicon and to have this electric backfield actually here to let the electron to avoid the electrons to go to the surface. Okay. So they will not be recombined at the back surface. However, to decrease the cost, you decrease the thickness of the wafer. And when you decrease the thickness of the wafer, when you make this firing high temperature step, because different values of thermal conductivity of silicon and aluminum, you can observe this bending of wafers. So that's a problem. Another problem is that at the interface between silicon and aluminum, at the surface, at this interface, you have many defects that will bring to other recombinations here of electrons. Okay. So it's a nice technology. We can reach almost 20% with this, 18–19%, but we cannot increase more the efficiencies. So the new technology that is the standard one now is what we call the passivated emitter and rear contact. What does it mean? What is the difference between the previous one? It's here on the back side. You can see that there is a layer between aluminum and silicon. This is a passivating layer that can be silicon nitride, silicon oxide, or alumina. This layer will passivate the surface, so reducing the possibility of recombinations. It can act also as a mirror to reflect the light, to to improve the possibility for infrared light to be absorbed into the silicon. Okay, and the contact between silicon and the metal will be localized. We make some holes here, and so by laser etching, and it's lead to an improvement of the efficiency from 19 to 20 and 21%. And this technology can be also used with multicrystalline wafers. No difficulties at all. So you can see that if you compare these two technologies, this one and this one, just presented here, and here's the efficiency of depending on these 4 technologies, depending also on the thickness of the wafer. You can see that you are able to increase the efficiency. Of course, you have more technological step, so it's a little bit more costly. But in the idea that what I said before, that we need, because we cannot, we need to decrease the cost of the energy we can produce. We need to increase the efficiency of the module. So we have to go towards this kind of technologies. And the last new technology is what we call the TOPCon technology. What is the difference between the previous one? Is at the interface here, you can see there is an oxide on all the surface of at the interface between silicon and the back contact. There is no hole. So TOPCon means tunnel oxide passivated contact. So there is no recombinations because there is no contact between silicon and metal. There is no defects at this interface. But we need a very, very thin oxide, only few nanometers. Okay? So there is different kind of TOPCon solar cell. This is the most standard one. So on the backside, you deposit your oxide, your passivation layer. Then you deposit polycrystalline silicon or amorphous silicon, anti-reflective coating also, your contact, and you make annealing also. So your amorphous silicon becomes polycrystalline silicon. Here you have a good contact, of course, between silver and high-dop silicon, but no contact with your silver or aluminum with silicon. So this architecture is based on the concept of carrier selective passivating contact. Recombination of minority charge carriers are suppressed by stacking thin layers of tunnel oxide and heavily doped polysilicon silicon. Okay. This leads to a significant improvement in the open circuit voltage. The choice of this oxide is there is many kind of oxides that can be used. The standard one is silicon oxide, but you have also aluminum oxide, titanium oxide, nickel oxide, and so on. Many possibilities. The choice of the oxide will depend on the type of material you have. It's P-type or N-type. It will depend on the temperature, the maximum temperature you want to use, etc., etc. And in 2022, in production, we already have some modules with 24, even 25% of efficiency. So very close to the maximum efficiency we can get in the lab, which is 27%. And here is the evolution of the technologies versus years. So in the next 10 years. So here in blue, it's aluminum back surface field. Here is the PERC, and now is the TOPCon times that are coming. Okay. So when a new industry wants to start business in photovoltaics, he has to consider what kind of technology is going to use. Of course, he will not use aluminum BASF anymore, but he has to think about PERC or TOPCon. There is some choice because you can see technology is changing very fast. When you have on the module one solar cell, so almost 20 by 20 centimeter, do you have any idea about the current that can be delivered by one solar cell? 1 ampere? It's 15 amps. Yes, 15 amps. For a 20 by 20, so 10 amps for a 15 by 15 centimeter. Yes, yeah. So it's this is a high current. You are not that you have to deal with. So you know from your first year of university that there is resistive loss in a device. It's Ri at the power of 2. So these losses are important because the current flow is very important. So to reduce these losses, what can you do? You can decrease the size of the solar cell. But actually, the solar cells, the size of the wafer are increasing. But so we fabricate the solar cell, and after we cut the solar cell in 2 pieces, like this. Okay, so we divided by 2 the current we are generating, but we divide by a factor 4 the resistive losses. Okay, so actually now most of the modules that you are buying are using half cells. Is it the case, Yves, for your PV installations? Oh, sorry. Okay. So you have different way to connect these cells, these half cells or third or fourth cells together. You can have this ribbon like this, but you can also superpose the edges of 2 neighboring cells like this. There is many work also going on to think about new contacts between solar cells. Okay. Okay. Another kind of solar cell, I would say a few words about this. This is what we call the bifacial solar cells. It's useless when you install the modules on your rooftop, of course, but in a utility scale power plant, it can be interesting because you can absorb also the light coming from the back side of the solar cell. Okay. So if you compare the PERC technology or TOPCon would be the same. With these bifacial solar cells, the only thing that is changing is that you have a grid not only on the front side, but also on the back side. And then you can have photons being absorbed from the bottom. It will increase not the efficiency of the solar module, but the production of electricity, because you get more photons than a standard module. It can be gained to from 10 to 20%, depending on the ground. If it is grass, the gain is not so high, but here you have many reflections from the soil. Okay. But it's interesting, okay, because you can combine the use of the land. You can generate electricity, but you can also use the land for agriculture, or for you can have some ships here. Okay, last but not the least, what will be the module that you can install by yourself within 10 years? The efficiency of the solar cell, silicon solar cell, is theoretically 29%. Okay. Why? Because you cannot absorb the infrared part of the solar spectra. Okay, or this part. And also because all the energy of these high energy photons are not transformed into electrons in an efficient way. You can see here you have high energy photons. It will generate electrons here, but at a higher energy than you need to go towards the conduction band. So this is what we call thermalization. This excess of energy is lost by production of heat. Okay? And then it is represented here. So all this gray part of the solar spectra cannot be used because of this. What can be used? It's a combination of 3 materials with 3 different band gap. So for instance, here, you have a large band gap here, a small band gap here. When the initial photons are arriving at the surface, so the blue one, high energy photons, will be absorbed by this high energy band gap. Meanwhile, the green and the red one with lower energy cannot be absorbed, and they pass through and reach the second material. So the green one will be absorbed, and then the red one will be absorbed by the last one. So it means that you don't have this thermalization losses, or not. So you still have some thermalization, but much more less. And then you can reach some very high efficiencies with this. So you have to connect your 3 cells. They can be connected by electrical contact, but this contact has to be transparent, of course. You can use also tunnel diodes to contact them. What is important here is that the voltage of the device will be the sum of the 3 initial voltage of each cell. Okay. However, the output current will be the same for the device, the 3 solar cell device, compared to the current will be the current of the cell producing the lowest current, because all these 3 cells are connected in series. So you have to design your device and to pay attention with the thickness of each cell to try to produce the same quantity of current into each cell to have the same current in each cell, and then to avoid the losses due to a bad current matching. Okay. So this is a IV curve and efficiency data of one solar cell. That it was a world record in 2009. It's quite old, but 41% efficiency. If you look at this data, if you look carefully, so you remember silicon cell, 0.6 volt. So here it's 3.1 volt. The current 1.6 amps, but the current depends on the surface of the cell. So you look at the surface, where is it? It's here, 0.3 square centimeters. So it's very, very small solar cell. Solar cell, very small, but still a current of 1 amp and even more. Why? Because we have this. This is the concentration of the factor, the concentration factor of the light. So we have a very small cell, but on the top of it, we have a lens, and we concentrate the light on this very small solar cell. So the effective surface of the device is not that this one, it's much more. So 40%, very, very important value. If you look at the detail of the fabrication of your device, you have many layers. It's a very complex solar cell. It's not only a PN junction. So you have a substrate, you have the medium band gap here and the high band gap here. You have to connect this by tunnel diode instead of transparent contact. You deposit each layer on the top of the previous one. So the people who do some epitaxy, they know how difficult it can be to deposit material on a different material. So sometimes you have some intermediate layers to adapt the crystalline parameter of the material. Anyway, you can have 2, 3, 4, 6 PN junctions, and then you can increase the theoretical efficiency. You can, I think there is some 6 junctions, 3-5 solar cells with 47% efficiency. But there are so many drawbacks with such technologies. First one is we have to, you should have the current matching, so same current in each subcell. So it means we should have the same amount of photons absorbed in each cell. But if you increase the number of junctions, it becomes more and more difficult. It can be simple in a laboratory to get this efficiency, but in the real life, when the sun is not exactly in front of the solar cell, maybe it's like this, then the absorption of the light, the repartition of the photons into the solar cell will not be as it was previously calculated when you have a normal absorption. Okay. So how we can simplify this technique and use all the development we did with silicon technologies in the past year. So this is what we call the tandem, the silicon-based tandem solar cell. So combination of silicon plus another material. So here is plotted the band gap of the bottom cell Here's the top cell band gap. If we use silicon, it will be 1.1 electron volt. And here is the efficiency of the tandem cell you are going to build. And you can see that there is an optimum here in red, so corresponding to a band gap of 1.7 electron volt for the top cell material. So you have to think about what kind of material we can use. So of course, we have many 3-5 materials that are candidate. Gallium arsenide phosphide. You adjust the composition of your 3-5 materials to adjust the band gap. But it's very expensive. So we can forget, we can avoid this. So the two main candidates today are CIGS. So CIGS, it's alloy of copper, indium, gallium, sulfur, and perovskite materials. So perovskite, as I mentioned, are a combination of organic and inorganic material. You have here the typical structure. Here you have the tandem solar cell we can make with combining silicon and perovskite materials. So we have this efficiency a few years ago that was improved very recently to 33%. Of course, on a very small solar cell, only less than 1 square centimeter. So this is still the drawback that we have with this technology. Only few square centimeter. And there is another problem, which is the stability of perovskite materials. The quality of this material is degrading with years. And it means that this efficiency will last only a few days or few months, but will decrease after a few years. And this is a big problem because silicon should last 30, even maybe 50 years. So you cannot add a material like this on the top that cannot work with the same during the same period, because if the perovskite is degrading and you decrease the current that is generated here, then you decrease the current that can flow into the silicon solar cell. So you will drastically decrease the efficiency. Another possibility is CIGS. CIGS, it's difficult to deposit directly CIGS on the top of silicon. So we need some interfaces. So one we are studying is gallium phosphide, a very thin gallium phosphide. So in collaboration with people in Rennes, Photon Laboratory. So we are working on this. You can see that we have very nice crystalline copper, indium, gallium, selenium, or sulfur on gallium phosphide, but still some troubles in the integration of all this on the bottom silicon solar cell. So a few conclusions, remarks to finish this talk, and what you have to remember and keep in mind after my talk. Of course, you can access the slides in the just after. Solar PV is now a mature technology. It's already a cheap technology. Thanks, and also it contributes to its large development. Then you can reduce the price. So it's very, very interesting. You can integrate PV in the electrical grid quite easily. There is still some innovation needed. So we need to increase, well, it's better to continue to increase the efficiency of the solar module. So by developing the tandem solar cell technologies, we can think about wider applications. For instance, modules that can be bended for a better integration in the walls, on the cars, etc., etc. Today, the major problem for development of PV is storage of the electricity you are going to produce. If you don't use it, you need to store it, so you need batteries. Well, I say it's a major problem. It's not a problem, but the quality of batteries has to be improved in the next years. Few words about what we call the terawatt objective. Today, I mentioned that each year we produce now 200 gigawatts of new modules. Within few years, we will reach the terawatt and tens of terawatts. It means that we need 10 times, 100 times more material to make these modules. So we need more silicon, we need more glasses, we need more aluminum, we need more silver. So we have to take into account the rarity of some materials. Silicon is not rare, there is no problem about this, but silver is it's a metal that is we are going to face troubles because of silver. So we need to replace silver by another metal. It can be copper, or it can be other kind of metal materials. It's possible. We can also use less metal to connect. If we reduce the size of the cell, we can reduce the current. Then we can reduce the size of the grid. We have to think about the life cycle of the module. So from fabrication towards end of life, recycling. I didn't have time to talk about this, but there is possibilities to recycle the module. At the moment, what we do with this, you take the module, you break into small pieces in dust, and then you have some high temperature thermal treatment, and you will be able to separate the several elements, glasses, so silicon oxide, silicon, and metals. But it's very difficult to reuse directly the silicon you get from these recycling materials, but it can be used for other applications. This is something that has to be improved. So another way to improve it is to think differently the module. So at the moment, because of the resin, you cannot separate, you cannot remove the solar cell after when you want to dismantle the module. It will be broken. So you have to think about a way to fabricate a module where you will be able to remove the glass and then to take out each cell very, very easily. It's possible. It's possible. When we talk about energy transition, okay, we think about carbon dioxide problem and so on, but there is also a very important problem, which is sovereignty. We need to reduce our energy dependency from other countries. So we could have a very good example this last year with Russian-Ukrainian war. And as I said, all the production, almost all production today is in Asia, especially in China. But there is many plans to reindustrialize Europe, not only for with PV, but there is plans for integrated circuits, for example, or for other technologies. So there is well, many things going on in this sense in France, in Germany, in all over Europe, in USA. Recently, maybe you heard about the plan decided by Joe Biden last year, this saying that we are going to cut the taxes for all the industry, green industries that will be installed in USA. So something very similar is going to happen in Europe. So a few words about the Carbon Photovoltaic project. So Carbon, it's a new company. Maybe you don't know about it, but it's investors from France who are going to create a new, they call this a gigafactory, because they are going to install a production line, so in the south of France, in Fos-sur-Mer. And the objective is within 2 years to be able to produce 5 gigawatts of modules and 25 gigawatts in 2030. So many employment will be possible with this factory. There are many other projects at the moment in Europe. Last words, I want to say that PV, and especially crystalline silicon PV development, was enabled by the strong collaboration between 3 actors. So academics, people from several fields of research, material science, chemistry, etc., etc. Industrial, allowing the transfer of technologies from other industry to optimize them for PV, and policymakers and society. So policymakers, we have incentive for early adoption and deployment of PV, especially in Germany from the 90s, in France from 2000 and something. But society, we need also that people require to use green energy for their electricity. And last but not the least, can remember that PV is only 5% of electricity in the world today, but in 2050 it may reach 40 to 50% in the world, which is very impressive, and it was very unbelievable 10 years ago. Well, thank you very much for your listening.